Welcome to another video on DEA or data envelopment analysis. This one we're going to talk about weight restrictions. So to motivate weight restrictions maybe as a solution to a problem, let's talk about one of the problems of DEA, which is as you add more metrics, more of your DMUs get rated as 100% efficient. And so if you want to measure your DMUs on many metrics, both for input and output, you either have to have a lot of DMUs that you're comparing, or else you're going to end up with everybody ends up being 100% efficient because they can do the best in their one niche metric for the input and one niche metric for the output. And so you want to be a little bit careful on how many metrics you use in your model. Okay. One way to get around this is to have more DMUs, but in absence of having more DMUs that you're evaluating, one way to get around this is by having weight restrictions. So this connects with the dual formulation. If we think about the dual formulation, we're thinking of efficiency as value of outputs over value of inputs. And we had these weights, V1, V2, U1, U2, which were sort of the value of each of the outputs and the value of each of the inputs. And we sort of said, our dual problem is we want to maximize the efficiency, which is the ratio of the value of output over input. And every DMU can kind of choose what it would like the values of the inputs and the outputs to be, as long as the efficiency of every other DMU still is less than or equal to 1. Okay, and then we turn that into a valid linear program. Okay, what we want to do is essentially put limits on the relative value of either our inputs or our outputs. And so we might say that one of our outputs is more important than one of our other outputs. And so we might want to say that V1 is not as important as V2. Okay, and we could even say V2 is more than twice as important as V1. And so we'd say that 2V1 is still less important than a V2. Okay. Important to for outputs, we're going to think of important as being more value getting out of it. We could also put weight restrictions on our inputs. And so we could say U1 is less than or equal to U2, meaning that it's U2 is more costly to us. And so we want to make sure that the cost of U2 is more than the cost of U1. Okay, for inputs, you want to think of those values as costs. For outputs, you want to think of those values as maybe revenue or something good. And so the better the output, the higher the value it is, but the better inputs are the ones with the lower value in some sense, or lower cost against you. Okay. And so we can add these weight restrictions. But these weight restrictions are happening as extra constraints in the dual problem. Okay, and so it seems to suggest that we should rather maybe formulate our problem in the dual problem instead of the primal problem that we introduced previously. And it also would sort of preclude us being able to use nice pre-built DEA software that sort of doesn't maybe necessarily have these weight restrictions built into them automatically. Until you think about it carefully and realize that a constraint in the dual problem is a variable in the primal problem. And so let's actually go back to the notes that we had kind of relating our primal problem up there and our dual problem down here. And let's add an extra constraint. And so I'll take this first constraint, 2V1 is less than or equal to V2. And I'll put that down as an extra constraint down here. Now, in the dual problem, I've got all my constraints set up as less than or equal to's. And so here's the column for V1 and V2. kind of had to write over them a couple times. And to make this into a less than or equal to, I'll subtract V2 over to the other side. And so then that becomes 2 in the V1 column and -1 in the V2 column is less than or equal to 0 on the right-hand side. Sorry, I don't have that in view, but zeros for the others. Okay. Now that's kind of interesting. It's another row in our constraint matrix for the dual problem. But if we think about this row in our constraint matrix correspond to DMU A, this one to DMU B, C, D. Here we had one for the denominator. That was sort of a special one. That one corresponded, well, let me actually maybe write the primal variable that each of these correspond to. And so this one corresponded to lambda A, lambda B, lambda C, lambda D. This dual constraint corresponded to our theta variable. What if we made this constraint here correspond to a DMU? Okay, not one of the 4 DMUs that we already have, but let's introduce lambda E, the weight for a imaginary or hypothetical DMU. Okay, and so we'll call this row DMU E. Okay, and then that other inequality on our weights, U1 is less than or equal to U2. We'll subtract U2 over the other side. And so that would put us a 1 here, a -1 here, 0, 0, less than or equal to 0. So 1 times U1, or 1 in the U1 column, try to get everything in the view there, -1 in the U2 column, 0 in the V1 and V2 column, 0 on the right-hand side, and we'll call this DMU F. So E and F are sort of imaginary DMUs. But what would those imaginary DMUs correspond to? Okay, and so kind of matching things up here. This column for each of our DMUs, if we look at one of these DMU constraints, we got negative of the inputs and positive of the outputs. Okay, so this DMU E, we can think of it as a DMU with no inputs, 2 units of Y1 and -1 unit of Y2. Okay, and so let's maybe bring this down and kind of write it here. And so this corresponds to a DMU E with X1 and X2 are both 0. And Y1 E equals +2 and Y2 E equals -1. Okay, so that's kind of weird to think about that we can have negative outputs, but yeah, it sort of works out with the constraints that we can make a fictitious DMU E with no inputs, but 2 units of output over here and -1 here. Okay, and then this one we can think of as DMU F. And it's going to have, let's see. So here, this one's the one that we need to be a little bit careful of. Looking at each of the kind of other rows, we've got negatives on the inputs. And so we get a -1 here and a +1 here. We need to kind of put negatives or multiply each of those by -1 to figure out what X1F and X2F would be. And so X1F ends up being equal to -1 and X2F equals +1. And then Y1F and Y2F are both 0. Okay, because they don't show up in that inequality. Okay. And so we can create a fake DMU that has some sort of, you can think of it, these DMUs, E and F, are providing for conversions between between outputs for DMUE or between inputs for DMUF. Okay. So let's go ahead and look at this in R and sort of see what happens when we add these weight restrictions. And I'll also give you sort of a rule of thumb to follow for these weight restrictions. So let me switch to share screen. Okay. And I've got this down towards the bottom. So this is going to be the same 2 input, 2 output model. And so I'll run that just to make sure. And here's sort of our reference and maybe our pictures. But now let's look at that same 2 input, 2 output model with weight restrictions. And so what we'll do is we're going to add fake DMUs to each of those. And so I'm realizing my notes here are not matching up with what I just gave as an example. So let me pause a second to fix those. Okay, I fixed my code to match what I had given in the example. So we want 2v1 is less than v2 and u1 is less than or equal to u2. To do that, we create a fake DMU E that has 0 for x1 and x2, 2 for y1 and -1 for y2. And then for fake DMU F for the second inequality on the weights or values with -1, x1, 1, x2, and zeros for both the y1 and y2. Okay, it took a little bit of trial and error, but here's sort of the rule of thumb that you can use to follow to kind of convert your inequalities here into fake DMUs is that you want to rewrite any input restrictions as an inequality with greater than or equal to 0. So this input inequality, we'd want to rewrite it as greater than equal to 0. So subtract the u1 over this side, and you have u2 minus u1 is greater than or equal to 0. And then we can rewrite and extract the coefficients of 1 for u2 and -1 for u1. And so that's where we get this -1 and +1. If you have an output weight restriction, rewrite the inequality with a less than or equal to 0. And so we subtract v2 over to the left side, and then we get 2v1 minus v2 is less than or equal to 0. And so we get a coefficient of 2 on y1 and -1 on y2. So you can do it sort of the way that I did it under the DocCam and kind of write the dual constraints and think about then what they need to be in primal constraints. Or you can kind of sort of use this rule of thumb that I kind of put together. So here we're going to create the fake DMUs. They end up being just extra values in this matrix. Be a little bit careful where you're inserting those values because unfortunately these the data for the DEA library wants to be a matrix and not something easier to work with like a data frame. Okay, so here's sort of a 5th and 6th entry for x1. Here's a 5th and 6th entry for x2. Here's a 5th and 6th entry for y1 and for y2. Okay, and I've given them a different name so that we kind of still keep the names in the data for x underscore input and y underscore output. And that's going to be kind of interesting because these extra DMUs are fake. And so we don't need to evaluate their efficiency. They should get 100% efficiency because they're the only ones sort of doing what they do. But we're going to supply those extra DMUs in what's called a reference set. So in the DEA command from benchmarking, we can give it inputs and outputs of the DMUs that we want to evaluate, but we can also give it inputs and outputs for DMUs that we're going to use to evaluate against. And so not every DMU that you're evaluating has to be in the reference set and vice versa. And so these extra DMUs go just in the reference set, but don't need to actually be in the original set. Okay, and we're going to keep things under constant returns to scale. It gets a little bit messier if we try to do variable returns to scale, because then we'd want to sort of change our conversion factor to be the right size, but we won't worry about that. So if we run this, now we see that C is efficient. D is actually no longer efficient. Kind of contrasting that to what was up here in our two input, two output model. We had that both C and D were efficient. But what you'll notice is that C put all of its weight or importance on output one, and none of it on output two. But now we're saying that output one, two times that has to be less than or equal to output two, and we see that's not the case for D, right? And so in putting this restriction on weights, we sort of said you got to value output two at least twice as much as you do output one, and D we see before we added that restriction wasn't doing that. So now we see that D is no longer 100% efficient. It's only 89% efficient. We get lambdas generated for A, B, C, D, E, and F. So anytime they're using the lambda for E and F, it means that they're sort of using that weight restriction. And so for A, we see that it takes as its example or target 21% of C, but then it also uses both of these weight restrictions are being applied to A. The weight restrictions don't affect C, it's still 100% efficient, but D is being affected by the weight restriction that we put on the outputs. And so now if we look at the U1 and U2, we'll see that now for A, we'll see that U1 and U2 are identical. It's the only one where sort of the input restriction was being applied. That was the DMUF. For output restrictions, those are being applied to DMUs A, B, and D. And so what we'll notice is that for D, if we double this, it's then equal to this. If we double this, it's equal to this. And if we double this, it's equal to this. If we double 0, it's less than or equal to this. So we said that 2 times V1 has to be less than or equal to V2. That was sort of already the case for C, but it wasn't the case for A, B, and D. And so by making V2 more important than twice V1, that sort of changed which DMUs were more or less important. I got the idea of doing this from an article by J.E. Beasley, and I'll quick kind of point over and see the interesting application of that article. And so let me pause and switch shares. Okay, so this is the article by J.E. Beasley. He's comparing university departments. Specifically, he was comparing chemistry and physics departments in the UK. And I thought it was kind of interesting that he included in the model for the outputs research ratings. And these research ratings were sort of included in the model as binary. And so there were sort of 4 levels of research ratings. Star was the highest, A+ was the next highest, A was the next, and A- was the lowest research rating amongst these universities. And what you'll notice is that each university was only given one of these ratings. And so it was kind of a hierarchy of ratings. If we use this in DEA by itself, then we would really only be comparing universities with the same research rating against each other because, there's in vanilla DEA, there's nothing to say that star is better than A+ is better than A is better than A-. Okay, but by one of the things that Beasley did in this article was impose weight restrictions that made the value of star 25% more valuable than A plus, and A plus 25% more valuable than A, and A 25% more valuable than A minus. And so it enforced this hierarchy, and by doing that, it reduced the number of efficient DMUs. If you hadn't put that restriction on the weights and the hierarchy of research ratings, then you would have gotten at least one efficient DMU in each of the different research ratings. So I thought that was an interesting application, and that would be one scenario where you have a categorical variable, essentially, is what this research rating is, and you want to use that in your DEA. Then you're going to have to sort of impose some sort of hierarchy on those categories. So that was an interesting application. That's it for this video on weight restrictions and sort of the trick of creating fake DMUs to enforce those weight restrictions.